Ionic or electrovalent combination. This is a force of attraction, that is, electrostatic force, between two oppositely charged ions, which have been formed by electron transfer. During an ionic or electrovalent combination, there is a complete transfer of electrons from a metal to a non-metal. The metal can easily give out electrons because it has fewer electrons in its outermost shell. Elements whose atoms have one or two valence electrons in the outermost shell require less energy to give away these electrons. Their ease in releasing these electrons in order to attain the stable duplet or octet structures makes them very reactive. Such elements readily combine with many other elements and compounds in their environment to form compounds. Examples are the alkali metals such as sodium and potassium. Each of their atoms has one valence electron to donate in order to attain the stable electronic octet. Calcium is comparatively less reactive since each of its atoms has two valence electrons. A greater amount of energy is required to dispose of the two electrons and attain the stable octet. Aluminium with three valence electrons is even less reactive, while carbon with four valence electrons does not transfer its electrons at all. On the other hand, non-metals like fluorine and chlorine are extremely reactive, like the alkaline metals. This is because each of their atoms has 7 valence electrons and needs to accept only one more electron to attain a stable octet configuration. Large amounts of energy are released during this process. In electrovalent combinations, after donating their valence electrons, metallic particles become positively charged, non-metallic particles become negatively charged after acquiring extra electrons. These charged particles are known as ions. The number of protons, that is the atomic number, is unaffected by the transfer of electrons that occur in an electrovalent combination. Therefore, the character of an element is unaffected by the chemical combination, since it is determined by the atomic number and not by the number of electrons. For example, the sodium atom, which donates an electron to chlorine in order to attain the stable octet configuration of neon, still contains 11 protons, whereas a neon atom has 10 protons in its nucleus. Let's go to our drawing board and demonstrate the formation of sodium chloride. During the formation of sodium chloride, the sodium atom loses an electron to chlorine to form the sodium ion with electronic configuration 2,8, which is the octet state that is stable, while the chlorine atom gains an electron and becomes 2,8,8, which is the octet state, to form the chloride ion. We can also illustrate this using dot and cross diagrams as follows. This is our sodium atom with electronic configuration 281. This is a chlorine atom with electronic configuration 287, and these are represented on the shells. Sodium chloride is an ionic compound. Here we can see the force of attraction between the positively charged ion and the negatively charged ion, which is the chloride ion. We can decide to show the combination using only the outermost shells. So sodium has one outermost electron. Chlorine atom has 7 outermost electrons. Sodium loses its 1 electron. Now this gives us 2, 8. So here we had 2, 8, 1. Here is 2, 8, 7. We can use another notation to show here that you have sodium with just 1 electron, chlorine with 7 electrons, this reacts to give this is a sodium ion. This is the chloride ion. Now let's show the formation of magnesium oxide. During the formation of magnesium oxide, magnesium atom loses 2 electrons to the oxygen atom and forms the magnesium ion, which is Mg2+, while oxygen atom gains 2 electrons to form the oxide ion, with electronic configuration 2,8. Now let's show this diagrammatically. Formation of magnesium chloride. During the formation of magnesium chloride, one magnesium atom is combined to two chlorine atoms. Here, the magnesium atom loses its 2 electrons, and each of the chlorine atom can only gain 1 electron. So, the first chlorine gains 1, the second chlorine atom gains the second electron. Here, this leads to the formation of magnesium ion and 2 chloride ions. Using the diagrammatic representation, we can have From the examples above, it is seen that ionic combination results in the formation of ions. These ions arrange themselves in a regular lattice. In the lattice, each ion is surrounded by ions of the opposite charge. The whole giant ionic lattice is held by electrostatic forces of attraction that occur between particles of opposite charge. Properties of ionic compounds. They have high melting and boiling points. This is because of the strong forces of attraction that exist between all the ions in the giant structure. They are crystalline solids at room temperature due to the regular arrangement of the ions in the lattice. They readily dissolve in water to form electrolytes, which conduct electricity. This is because water is a polar solvent. and so charged ions can move about in it. They conduct electricity when molten or in solution, as the ions will be free to move and carry current. They do not dissolve in organic solvents like kerosene because they are mostly inorganic compounds.